We will now discuss devices that are based on piezoelectric resonance or resonance properties of piezoelectric devices, or in general operation at high frequencies. I did forget to mention when we were discussing piezoelectric motors that many of them are in fact piezoelectric ultrasonic motors, and the book by Yushino that I recommended to you is actually called Piezoelectric Actuators and Ultrasonic Motors. Not just motors. However, these motors, even though they operate at ultrasonic frequencies, the final motion of the device can be at well below sub-resonance frequency. So you will see that in the Yushino's book if you read it. So the first device that operates on the principle of piezoelectric resonance are biosensors, thickness monitors, and nanobalances. There are other applications, and these are devices that, based on the piezoelectric resonance on its shift, can determine very, very small amounts of material. It goes down, I think, with the latest versions, down to picograms of a material. So how does it work? You have a piezoelectric sensor, and on that sensor, for example, you can put a selective coating, which is sensitive to only some species that are present in the atmosphere, which can be gas or liquid, above that piezoelectric sensor with the coating. This coating will absorb molecules, species that you want to detect, and that will change the total mass, which is resonating. And remember, piezoelectric resonance is proportional to the density of the resonator. So if the density changes, effective density changes, that will mean that frequency will be shifted, and this change in a shift of the frequency, if you know what you are depositing, can be related to the mass of the species that you are depositing. This can be quantitative or qualitative. You just want to detect certain species, or you want to also determine their amount. As a thickness monitor, you would you have your substrate on which you want to deposit a thin film. You start deposition, and next to your substrate you put a quartz sensor on which you are depositing the same material that you are depositing on your substrate, and from the shift in the frequency, you can, if you know the density of the deposited material, you can actually calculate thickness of the film that you are depositing, and this works reasonably well. So besides thickness monitoring, you can detect toxic gases, for example. You can detect blood groups in the blood, and you can even detect presence of viruses. Of course, viruses are too small to be detected, but what you do, you detect antibodies specific, for example, for HIV virus. For these applications, you would use piezoelectric materials that have a very high mechanical quality factor. Mechanical quality is, if you look at resonance as a function of a frequency, then the sharpness of the resonance determines the mechanical quality. And if you use single crystals, such as quartz, you would usually get a very sharp resonance, and the mechanical quality is the resonance frequency divided by delta F. where this is delta F at a half maximum, while in a PZT, while resonance may be bigger, this mechanical quality is much lower, so shift in the resonance is much more difficult to observe. So you need high quality, high mechanical quality resonators for this. You will find this is a continuously developing area, and I think people have now shown that you can go down to picograms detection. Other ways in which ultrasonic in which piezoelectric resonance can be used is for detection and imaging with ultrasound, and that works in the following way. You have a piezoelectric transducer, so it's piezoelectric element that you would make resonating at a certain frequency. Through the converse piezoelectric effect, it will emit acoustic wave, which will come to an object which you want to inspect for presence of in medicine, for to see, for example, a baby, or presence of cracks in some bridge, in a metal piece of metal, presence of porosity, corroded surfaces, and so on. In medicine, you can also detect foreign bodies, you can detect cancer, and so on. So your acoustic signal comes, it gets reflected at each surface which it meets, and from the intensity and the contrast you can of the reflected wave, you can create an image, analyze it, and this can be so good that you can actually do diagnosis, not only imaging. That reflected sound will create a pressure wave, which will come to the same piezoelectric transducer, and then through direct piezoelectric effect create this signal that I just mentioned. So the applications are medical imaging and diagnosis, material testing, porosity, density, interface, cracks. Then there is series of object detection, proximity sensors, distance measurements. This is used, for example, in cars for parking sensors. You can use an optical camera, which is very nice, but the optical camera cannot detect if you have transparent surfaces, while ultrasound can do that. So the best way is to use both ultrasound and optic detection. And then you can go on and detect blood flow, velocity of the blood, using Doppler effect. This is very useful to detect whether there are any foreign bodies in the blood vessels, and detecting of a blood flow during surgery, for example, in the brain. So how does this Doppler effect works? Well, you will have a catheter which goes inside blood vessels. So these are very small catheters, less than 1 millimeter in diameter. This is a piezoelectric transducers. It is brought into resonance. It emits acoustic wave, which goes through the blood. Blood is flowing with some speed. This sound wave will be detected, come back to the same transducer, produce a signal there about a frequency of the incoming and the reflected wave will be different, because the medium blood in which acoustic signal is propagating has its own velocity, and you know from physics that if acoustic wave is moving, propagating in a medium that has its own velocity, or if a source of the sound is moving, then the frequency will change. So the change in the frequency is proportional to the velocity of sound in that medium, and or inversely proportional to the velocity of sound in that medium, and directly proportional to the velocity of the medium, or velocity of the source with respect to the medium. So you will emit a pulse and then monitor these properties. And then if you know delta F, difference in the frequencies, you can calculate V, velocity of the blood in this case. And that's very important during surgery. You want to monitor whether blood is flowing through some blood vessel or not. For example, for a brain surgery, you can do this outside in a non-invasive way, monitor blood flow, and that's very helpful to a surgeon. Or you can use it to detect whether there is a clogging of blood vessels, for example, with the fat deposits. If you have a fat, if you don't have fat deposits, you will have a nice, almost Newtonian movement of the blood. But if there are if there are deposits, then there will be creation of a turbulent flow. And if you monitor velocity over the time, the signal will be different, and from that signal you can calibrate it and detect whether there are obstacles to the blood flow. So these are very popular, very useful, and used a lot in for monitoring in surgery and so on. Now, to understand how this works, we will to understand how this works, we need to understand an important parameter to consider in this ultrasonic imaging is so-called acoustic impedance matching. And this is similar to electric impedance matching in electrical circuit, and also what's happening in the optics. So if you have incident wave moving in one medium and it gets reflected in another medium, and it gets reflected from another medium, you will have reflection and you will have transmission. You will have transmission into this second medium, and you will have reflection in the to the medium where your incident wave is coming from. And if everything is reflected, if the whole acoustic energy is reflected, you will not be able to expect what is happening in your sample. So you should have some transmission into the second medium. And how much you will have reflected and how much transmitted depends on acoustic impedances of two media. Acoustic impedance Z is defined as product of the density of the medium times velocity of the acoustic wave in that medium. And the acoustic density is proportional to Young modulus and density of the medium. Now, it turns out if you look at ratio of reflected to incident beam, and let's take it, it's given by this, so it's similar to Snellius law in optics. Let's look for perpendicular for a normal 90-degree onset. So we have here an angle of 0 degrees. We find out that the ratio of reflected to incident beam is proportional to the difference in acoustic impedances. So if two acoustic impedances are the same, so two materials have similar acoustic velocity and similar density, you will transmit most of the acoustic energy to the second medium. If they are so there will be very little reflection. If they are very different, then you will have a lot of reflection, and that is not good. So if you have a piezoelectric ceramic which has a very high density and very high acoustic velocity, with respect, for example, to human body, and human body has acoustic properties of water, more or less. So ceramics are very dense, the speed of velocity of the sound is very large, while human body has a very low density of 1. And so if you put piezoelectric ceramic and excite it into vibrations on a human body, very little of that acoustic energy will move into body. Most of that will be reflected because you have a very large impedance difference. We say that impedances are not matched. If impedances are the same, we say that impedances are matched, and then there will be a good transmission. And then, of course, you come to another surface that you want to detect, and then you want to get some reflection. Talking about this, you will need to match impedances of your acoustic transducers, of your piezoelectric transducer, and the body in which you want to expect. If you are expecting a piece of metal, then there will be a good acoustic matching between piezoelectric ceramic and human body. If you have if you want to inspect biological matter, human body, then there will be a large difference. And there are ways how to compensate for this. So to give you some examples, the units of impedance, acoustic impedance, are given in what is called megarails, and for piezoelectric ceramics you have between 20 and 30, even higher than 30. For water, for human tissue, the acoustic impedance is about 1.5 megarails. So here are different ceramic materials. This is PVDF and it's copolymers, and this is 1,3 composite. I will explain that later, but it's a composite of ceramics and the polymer. And you see that acoustic impedance for ceramics is very large, for polymer is, as expected, very low. And for 1,3 composite is intermediate. Now, coupling coefficient, the parameter which tells you how much of the energy is transformed, which is the most important parameter in transducers, is very low in the polymers, is large in ceramics, in PZT, for example, and can be very large in 1,3 composites. So even though impedance is not as well matched to that of human tissue, the coupling coefficient is very large, and that compensates. And also what is important, as you will see later, is the dielectric permittivity, which depending on the transducer should be either large or small. And you also see that the density of composites is closer to that of water, which is 1 than that of ceramics. So these composites really work very well. Polymers, on the other hand, are the best to transfer acoustic energy from piezoelectric material into air. So you would use piezoelectric polymers to detect, for example, explosion in the air, while for imaging, 1,3 composites are the best. Now, there are some tricks that you can use to improve this acoustic impedance matching. And if you just consider normal incidence, then for a reflected and transmitted wave, if you have a two media, one with the incident wave and one in which you want to transmit, reflective and transmitted waves are given by this these formulas. However, you can add a matching layer which has the properties between this one and that one, and if you manage to make the thicknesses, so these are thicknesses of these different layers, which need to be comparable to the wavelength of the acoustic wave, you can actually improve this much more. So here is thickness from 1 to 2 if you have a third layer, and this is from 1 to 2 if you have only 2 layers, and you can look a little bit into these relationships. So when you go to ultrasound imaging, they will usually put some kind of gel on your body, and this gel has, among others, role to improve this transfer of acoustical energy from the transducer into your body. This is very similar to electrical impedance matching. So if you have here a source and you want to put electrical energy into load, for example, in speakers, you have to match that resistance of source and load are as close as possible. So the impedances have to match, and the power delivered to the load is given by this, and you can find out that the maximum power is obtained when load and source have exactly the same impedances. And the same way it works with acoustical impedance matching. So for transfer of energy, these are similar concepts. Before we go to the next part and discuss application in medical imaging and these composites that we are using, we will make a break here.